I am Walter Lewin, and I'm going to teach you a little bit of physics at the request of your own physics teacher, Jason Hafner. We really don't have the right equipment for this, so it's highly improvised. But the goal is that I want to cover with you something that is the most intuitive of all of electricity and magnetism. So non-intuitive that almost all college physics books have it wrong. Why do they have it wrong? Because the physics teachers do not understand Faraday's law. Yeah, you may be embarrassed to hear that, but it's true. Almost all physics books have it wrong. I would advise you to watch my lecture 16. Some of that I will cover now, but you definitely have to read my lecture note of lecture 16. I have here a simple circuit with two resistors. One resistor, which I call R2, and the other resistor I call R1. All the wires here have no resistance. Superconducting wire. We have that at MIT. You may not have that at Rice, but we have that at MIT. Perpendicular to the blackboard, we have an electromagnet, and we can turn that electromagnetic on. That's all I'm going to do, because the physics when turning it off is very similar, so I will only discuss with you when we turn it on. So the magnetic field goes up very rapidly and then stays constant. And let's assume that that magnetic field is pointing out of the blackboard. I could have chosen into the blackboard, but I will take out of the blackboard. As long as the magnetic flux, and the magnetic flux is defined as the integral of the magnetic field B dot ds over an open surface. It's very important, an open surface, and that open surface I will attach to this closed loop. And you may choose that surface any way you want to, but I want it to be attached to this closed loop. I call this point here A1, this point here A2, this one D2, and this one D1. I want you to understand and appreciate that A1 and A2 from an electrical point of view are identical, they are the same, but are connected to a wire that has no resistance. So you can think of A1 and A2, if you want to, simply as A. They are one and the same. You will see there's a reason why I split them. And the same here. D1 and D2 are also the same. So you can think of this as one point A and one point D if you want that. When the magnetic flux, the way I defined it, is changing in time, according to Faraday's law, the closed loop integral around this circuit is not zero. If the closed loop integral of E dot dl is not zero, that means that Kirchhoffs loop rule does not work, cannot be used. Using it is absurd. Kirchhoffs' loop rule would say that the closed loop integral of E dot dl, the closed loop integral of E dot dl would be zero according to Kirchhoff. I start here and I go all the way around and I come back here and that should be zero. But that's not the case. If there is a changing magnetic flux, the way I defined it. The answer, according to Faraday's law, is that this is minus d phi, the B makes use to the magnetic field, dt. If the magnetic field is increasing, because I turn it on all of a sudden, the magnet, then clearly the magnetic field is not constant, magnetic flux is not constant, so I'm going to get an integral E dot dl that is no longer zero. We call that also often the EMF, electromotive force. Therefore, there is a current going to run, and you can figure it out for yourself, because I'm sure you will cover this in class, that in this case, when the magnetic field is increasing, and therefore the flux is increasing, that the current is in this direction, the current I. And so this EMF, which is this integral, equals I times R1 plus R2. So we just looked at our first 8 minutes, and we noticed that the red color that I'm using, which works so well at MIT in 26100, with this camera didn't come through so well. And so whatever is red here, which was I for current, was this arrow, I will put them in white. I wish I didn't have to, but I will do that, otherwise you may not see them. So the current is going around like this. If that B field pointing out of the blackboard is increasing. Now, what now is the potential difference between A2 and D2? Between here and here? Or I could say, what is the potential difference between A and D? Because we agreed we can call this point A and we can call this point D. So the potential difference, V, A2 minus V D2 is the same as VA minus VD, because A2 is A and D2 is D. And that must be I times R2. Very simple. What now is the potential difference between A1 and D1? Which of course is also the potential difference between A and D. So, the potential difference between A1 and D1, which is also VA minus VD. Now be careful. The current is in this direction. So this point has a lower potential than that point. So it is not I times R1, but it is minus I times R1. Because I go from here to there. I oppose the current, whereas here I went with the current. So it is minus I R1. Now, it's staring you in the face now that Kirchhoffs loop rule is for the birds. Because if I measure here VA minus VD, then I get I times R2. If I measure it here, which are the same points, I get minus I times R1. They even have different polarities. In other words, if I would put here a voltmeter, V1, that voltmeter would measure this value. And if I put one on the other side, for which I have little room anymore, that would measure this value. And the voltmeter on this side, I will call V2, and I will call the voltmeter on this side V1. And so what you see now is that V2 divided by V1 is minus R2 divided by R1. Think about this for a minute. Both voltmeters, this one and this imaginary one that I haven't drawn, they both measure the potential difference between A and D. Both voltmeters I will have plus up and minus down. I will do the same here. If the ratio of these resistance is 100, then one voltmeter will read a value which is 100 times larger than the other voltmeter, but not only that, the polarity is reversed. So this one might read plus 10 volts, this one might read minus 1 volt. So it's now staring you in the face how non-intuitive this is. I can give you an example by making certain assumptions. Suppose I have R1. I think I chose 10 ohms. And I have for R2 100 ohms. And let us assume that at a particular moment in time, this induced current, it's induced by this changing magnetic flux, that induced current at that moment happens to be 10 milliamperes. Keep in mind, it will change with time. Why will it change with time? Because the EMF will change with time. Why will the EMF change with time? Because d phi dt will change with time. I cannot keep the change of the magnetic flux constant all the time. So let us assume that at a particular moment, this induced I, which changes with time, is 10 milliamperes. Then you see that this voltmeter on the left side, V1, will read 10 milliamperes times 10 ohms, that is minus 0.1 volts. Minus, keep that in mind, it's minus. This voltmeter, the plus is here and the minus is here, will read a negative value. A has a lower potential than D. But V2 will read 100 times 10, 1 volt. And I do this experiment in my lectures. You will see it if you watch lecture 16. And you won't believe your eyes. And I will show you, we'll have a small break now here for our 8 minutes. I will show you what actually you will see on an oscilloscope when you put an oscilloscope here for V1 and at the same time you demonstrate here the oscilloscope which shows you V2. So we're going to put that on the board very shortly. I want to repeat once more that the larger the value of d phi dt is, the larger the EMF. If the magnetic field is increasing, then the current will be in a different direction, the induced current, than if the magnetic field is decreasing. But those are details that Jason will discuss with you. That's not really, at this moment, so important. So let's now assume that the EMF is in this direction, that the current is going around like this, and I'm going to make you now a sketch of what we will see. Look what I did in the meantime. I cleaned the blackboard, and so now I have a nice opportunity to add that voltmeter V2. Here is the plus side of V2, and here is the minus side of that voltmeter. So they're both hooked up in exactly the same way. They both measure the potential difference between A and D, and they both get totally different values. Let me make a drawing, a sketch of the magnetic field, which is not the magnetic flux, but simply the magnetic field that we produce in the lecture hall as a function of time when we turn on the electromagnet. I make some rough guess. It starts with 0 and then it goes something like this, and then if we keep the magnet on, then of course the magnetic field will reach a maximum and will flatten off. Notice that here dB dt is 0. So there's no longer any flux change. But here it's almost constant. There is a flux change. Let us first do V2. And this means plus. So I would say between these 2 points, between here and here in time, the flux derivative is roughly constant, because this is almost a straight line. And so it means that V2 will have a certain value. In our case, the example that we chose, V2 was, what was it, 1 volt? Yes, I think so, plus 1 volt. That's why I have it at plus. And when you hear, the d phi dt is 0. So you must end up here again, and I will just somehow sketch it, then it gets down to 0. So that's what you will see on the oscilloscope. Then we show the students at exactly the same time, we show them V1 as a function of time. And since V1 is negative, I can use the same scale, the same vertical. Now, in our special example, V1 was 10 times smaller and negative. Well, 10 times smaller is something like this. So you'll get something like this. And so, the moment that we turn on the electromagnet, we show the students as a function of time, millisecond resolution, V2 and V1, and these are the curves that you will see. You see in front of your eyes the fact that 1 voltmeter, in this case, reaches a 10 times larger value than the other, but also that the polarities are reversed. When I did this experiment, in my audience was my good old friend very bright physics professor, Bob Ledoux. This was a long time ago. It was 1992, I think. And Bob came to me after the lecture and he says, Walter, this cannot be. There must be something wrong. I said, Bob, I don't think so. Give it some time. I went to my office and the phone rang. Who was on the phone? Bob Ledoux. He said, Walter, I can't believe it. It's true. You see that even for physicists, this is not so obvious that the potential difference between 2 points measured one way and measured another way, between exactly the same points, totally different in value and different in polarity. And so I really want you to watch this on lecture 16, and I want you to read my lecture notes on number 16. If Kirchhoffs' loop rule were to hold, which it doesn't, then V1 and V2 should always measure exactly the same value. I hope you realize that. So you see, to use Kirchhoffs' loop rule here is not even wrong, but it's criminal. You get nonsense. But Kirchhoff would predict that the potential difference between here and here and here and here is the same, so that the closed loop integral of E dot dl then becomes 0. Alright, you have something now to think about, and now I will again stick with Faraday's law, but change the topic a little bit. So maybe this is a good moment for Safe to have a break, and I will clean the blackboards. I will show you a very simple circuit in which I put a solenoid, a self-inductor as we call it. It is an ideal self-inductor, and what that means is that the self-inductor is made of superconducting wire, so the self-inductor has no resistance, and that means that there can never be an electric field inside that self-inductor because the resistance is 0. So keep that in mind. Ideal self-inductor, that the wires have no resistance, there can never be an electric field in a self-inductor. I have here a simple battery. I chose just a simple battery rather than an alternating current because I'm sure that Jason will cover with you these circuits with alternating currents. I just want to stick to the very basics. So here is a battery, and here is a resistance R. Here is a capacitor C. Here is a self-inductance L. And then we close the loop, and we have it here, and in here I'm going to put a switch. So self-inductor, which has no internal resistance, the wire is a superconductor, capacitor, resistance, and let us assume for simplicity, although it's not important, that the battery has no internal resistance itself, or negatively small, and let's assume that the value of the battery is V0, so it remains constant. I throw the switch. Obviously, what's going to happen? A current is going to flow in this direction, because this is the positive side. So I wish I could do it with red, but that doesn't work so well on the camera, so I will do it then with white. So a current is going to run in this direction, through the resistor, in this direction, through the self-inductance, in this direction, in this direction and in this direction. Now, what does Faraday say? Faraday says that the closed loop integral of E dot dl equals minus d phi dt. The magnetic flux is through an open surface, as I discussed earlier, and that open surface must be attached to your closed loop. So the closed loop is this. And so we must attach a surface, think of it as a soap film. It doesn't have to be flat, it could be curved, it could be changed, very strange in shape, but it has to be an open surface that is attached to the closed loop. And if you want to see how that looks inside the self-inductor, it's very hard to see. It becomes almost like a staircase that the soap will run around. Because it must be one open surface. Alright, now we're going to write down the integral of E dot dl. I really want to try with a different color. And if it doesn't work, then Save will tell me. Do we agree that the E field here is in this direction? Can you see it or not so well? The E field is in this direction in the resistor. This side of the capacitor will become plus because of the current flow, and so the E field here is also in this direction. What is the E field in the wire of the self-inductor? What do I hear? What are you saying? It's zero! Exactly, because there is no resistance. So E here is zero. So the integral E dot dl through this wire is zero. The E field here goes from plus to minus, so the E field here is in down direction. So now we are ready to write down the differential equation for this circuit. And I will start at this point, I will go around, and I will come back at this point. So the first value, when I go in this direction, is minus V0. Right? This is the integral of E dot dl, the angle between the two is 180 degrees, so I get a minus sign. In the resistor, it is plus I times R. I changes in time, but at a particular moment in time it happens to be I. Remember the capacitor, C equals Q divided by V. I call this V of C, and so we get plus Q divided by C. That is E dot dl over the capacitor. Yeah? C is Q divided by V, and so the potential difference, which is after all the integral of E dl, this Vc is C divided by Q divided by C. Now I come to the self-inductor. And I'm crawling inside that wire, and I go through that wire, and I never see an E field. I never see an E field. In other words, the integral E dot dl between this point and this point is zero. So, I am back here now at this point where I started. So according to Faraday's law, that is minus d phi dt, for which Jason will tell you that that is the same as minus L di dt. I will not explain why this takes this form. I can't take that away from him. He's dying to explain that to you. So look at this equation now. This is the closed loop integral of E dot dl. That, according to Kirchhoffs, would have to be 0, but it isn't. It is minus L di dt. Now I'll tell you that almost all college physics books cheat. They do it wrong, but they get the right answer. Why do they get the right answer? Because they know the answer. They write the following. They write in their book, oh, I should make sure that this is. They write minus V0 plus IR plus Q divided by C plus L di dt is 0. So this is the honest way it should be written, according to Faraday's law, and this part is the closed loop integral of E dot dl. The college physics books, most of them are written by physics teachers who do not understand physics, they write it this way. And then they say, do you know why this is 0? Because of Kirchhoffs. They say, look, this is the closed loop integral of E dot dl, and that has to be 0 according to Kirchhoffs. This is not only wrong, but as I said earlier, it is criminal. Because this is not the closed loop integral of E dot dl. This is the closed loop integral of E dot dl. And that is not 0. So the simple fact that they put this term here doesn't make the equation wrong, but the physics stinks. And this is very, very serious. Because if you start teaching students a concept that is completely wrong, well, I have to calm down now, but this is emotionally very important for me. I would advise you to also read, definitely read, my lecture notes number 20. So I imagine by now you're awfully confused, but at least you know, you've seen once, how to do things the correct way, correct in terms of physics. The fact that these two equations give the same answer, well, of course, because the authors of the book know the answer. I'm now going to cause you some sleepless nights. And I'm going to attach here a voltmeter. And now I'm going to ask you, what will this voltmeter show? And you will probably say, well, didn't you say that integral E dot dl through the wires here is 0? So you would think that V here is 0. But that's not true. You know what that V is going to be? It's going to be plus L di dt. In other words, this equation is now correct. And you will say, now what happened now with your phi dt? Well, what I have done in a clever way, by going around the circuit, I have now no longer any changing magnetic fluxes going through my open surface, which is now attached to my new closed loop. And my new closed loop, follow me, is like this. And look, when I come here, I bypass that self-inductance, I go through the voltmeter, and I come here, and I come here. And so now, Kirchhoffs' loop rule should hold, and so the sum should be 0. Therefore, it shouldn't surprise you that this plus L di dt is exactly what this voltmeter then will show. I'm going to confuse you even more. I'm going to remove this voltmeter. And you hold in your hand an instrument to measure the electric field E. And you start here, you go around and you get this term, you get this term, you get this term, and now when you arrive here, you leave the circuit and you go this way. You can choose your path, I don't care. And you come back to the circuit here. But while you are going this dotted line, which could be just through the air like this, you measure the integral of E dot dl over that path that you have chosen. And what will that integral show? Plus L di dt. Again, you have now chosen a loop whereby there is no longer any changing magnetic flux going through that surface, and so Kirchhoffs loop rule works. I would like Jason to discuss with you why it is that that voltmeter would measure plus L di dt, because clearly the L di dt has to do with this self-inductance. So I leave that up to Jason. Gonna leave something for him. So before I go off the air, I would like to say a few words to the many people who are now taking this course, this edX course, which is taught by Jason. I would like to many of you who may also have taken my 801X course. Almost everyone who took 801X seriously passed the course, more than 85%, for those who took it seriously. So my advice to you is, to all of you, maybe tens of thousands all over the world, who have been following this course, this edX course, this electricity and magnetism course, if you take it seriously, that means doing your homework seriously, work hard on the exams, you too are probably, very likely, going to pass. I wish you good luck.